Okay, let's take a look at page 21, which is about percent yield. And to talk about percent yield, we're going to start with an example of how to herd cats. Okay, when we do calculations in stoichiometry, those are based on ideal reactions, meaning if the world was perfect, this is how it would go. But many reactions do not go to completion, meaning they don't actually finish happening all the way, and not as much product is produced as expected. You don't end up getting as much as you think you should get. So we're going to look at a real-life example, herding cats. Miss Lustig, that's a teacher down the hall, is trying to herd 200 cats from her home in Austin all the way to Round Rock High School. In theory, in a perfect world, how many cats should make it all the way to Round Rock High School? Well, in a perfect world, all 200 cats would make it. That perfect world scenario of 200 cats making it, that's what we call the theoretical yield. Theoretically, if everything was perfect, if everything was sunshine and rainbows, then all 200 cats would make it. But in the real world, how many cats make it? Probably not all of them. Cats are notoriously hard to get to do anything you want them to do. They get distracted, they climb trees, they chase mice and squirrels. Hopefully they get out of the way of cars, but if you're trying to take them all the way up I-35, then probably some of them won't make it out of the way of the cars. Cats are going to escape. Not all of them are going to make it from Austin all the way up I-35 to Round Rock High School. So in the real world, maybe only 189 cats make it. That's the actual yield. That's our sad crying rain cloud, where 11 cats didn't make it. Something happened and they're gone. So percent yield is what we calculate when we take the actual yield divided by the theoretical yield, multiply it by 100 so that our decimal changes to a percent. So you take your sad number that's not as many as you want divided by the perfect world scenario, sunshine and rainbows if everything was golden, times 100. So in this scenario, 189 cats actually make it, divided by the 200 cats that theoretically should have made it, times 100, and we find that 94.5% of the cats made it to Round Rock High School. Let's try a second scenario. The chemistry team tries to herd 75 of those cats from the 600 building down to Mr. Groff's office so he can have a nice surprise. But only 73 of the cats make it. What's the percent yield? Well, 75 cats, that's our sunshine and rainbows perfect world scenario. This is me attempting to draw a rainbow, okay? Only 73 cats make it. That's my crying rain cloud scenario, where, you know, I guess 2 cats just, they got distracted by a squirrel, they found some trash they wanted to play with, I don't know, whatever. So what is our percent yield? We take the actual yield, how many actually made it, which was, in this scenario, 73, divided by our sunshine and rainbows perfect world scenario, which in a perfect world all 75 would have made it. You divide those out, you'll get a decimal that you multiply times 100 so that it turns into a percent, and 97.33% of the cats made it to Mr. Groff's office. So let's take this idea and bring it back to chemistry. Just like cats, not all atoms from the start, not all of your reactants, make it to the end to become products. In theory, in a perfect world, 100% of the reactants become products. But in actual labs, they don't. So to find the perfect theoretical yield, we need to use stoichiometry. You're going to have to do a mole bridge. Yay, mole bridges! So if we're going to find out how much stuff we should have made, we're going to have to do stoichiometry first. In an actual lab, not everything becomes a product. Some stuff doesn't mix well, some of it gets like left behind in a beaker or something. to find the actual yield, we have to know what amount was produced in the lab, and that will be given to you in the problem. We will always tell you the actual yield. Okay? So you have to use our formula. The actual yield they will tell you in the problem. The theoretical yield you have to find with the mole bridge. Let's mark that down. The actual yield is given to you in the problem. The theoretical yield you have to find with a mole bridge. And then you'll, of course, still multiply by 100 after you divide those. I want to make a note for you here. The word yield means made or produced. So a yield is always going to be a product. That's important. We'll look at it in the next problem, but keep that in mind. A yield is always going to be a product. When you're trying to identify in the problem what is your given actual yield, it's going to be the one that's a product. The word yield means it was made or produced. It's got to be a product. So we go look at page 22, number 1. It says calculate the percent yield for the reaction above if 534 grams of carbon dioxide react to produce 645 grams of carbonic acid, H2CO3. So they're telling me I have 534 grams of carbon dioxide. We're making 645 grams of the H2CO3 carbonic acid right there. They want to know the percent yield, which means we need the actual yield divided by the theoretical yield times 100. I'm abbreviating. I hope that's okay that I abbreviate. Remember, the actual yield will be given to you. The theoretical yield you have to find from a mole bridge. They gave us two numbers, so how do we know which one's the actual yield? Well, if we look at back at the bottom of page 21, a yield will always be a product. A yield will always be a product. So that means of these two given numbers, the one that's a product is going to be my given actual yield. So that means this 645, that's the actual yield, because that is for a product. That's on the product side, the right side of the arrow. So, let's break down this problem. If we want to find the percent yield, we know our actual yield that we're going to put on top, but we need to know the theoretical yield. So, I know the percent yield is going to be the 645 grams that was the actual yield that they gave me. It's got to be divided by something times 100. We got to find this something, this theoretical yield. And the theoretical yield is something that we find by doing a mole bridge. So we have to find how many grams of the product are produced as the theoretical yield from the given reactant. That's the mole bridge we have to do. Remember I said the theoretical yield, you have to follow a mole bridge. Well, they gave me a reactant. I'm going to follow the mole bridge to find grams of the product, and that will be my theoretical yield. This 534 is not my theoretical yield because 534 is a reactant, and remember, a yield will always be a product. So I have to use the reactant to mole bridge to the product, and that will get you the theoretical yield. This is a T. Doesn't really look like one. You use the reactant to mole bridge to the product, that gets you your theoretical yield. So here's my reactant. I'm going to mole bridge to the product. That's going to get me my theoretical yield. We were given grams of the reactant. We have to find grams of the product. So grams and grams, that's going to be a 4-fraction problem. Remember to start your first fraction all the way to the left or you're not going to have enough room. Our given that we're starting with for this bridge is 534 grams of CO2. We're going to put that over 1. We already drew the bridge, so our next stop is what goes up must come down. Remember, your number of grams is going to come from the periodic table. So we could, I'll do it up here, calculate 1 carbon, 2 oxygens. If you check your periodic table, the mass of carbon is 12.01, the mass of oxygen is 16, and if you add that all up, the mass of carbon dioxide is 44.01 grams. So that's going to come down here. I'm not ready to use the bridge yet because remember, this bridge is a mole bridge and I'm in grams right now, so I can't use the bridge yet. But if I change this to moles, then hopefully I'll be able to use the bridge later. And if we look back to our notes on page, like, where was it, 12? No, page 11. On page 11, we talked about how if you have grams and moles in the same fraction, we go back to doing it the old way, 1 mole, and the grams are from the periodic table. So we already did grams from the periodic table. This is going to be 1 mole. Then I do what goes up must come down, so moles of CO2 are going to be on the bottom. And now, whenever you get to a fraction where for the first time you have moles on the bottom, that's when you follow your mole bridge. So I go back up and I look at my bridge. There's only, there's not a number in front, that means there's 1 CO2 here. I follow the bridge, it's pointing at H2CO3. If there's no number in front, that means there's 1 H2CO3. And remember, the bridge is always moles, so this is going to be moles of H2CO3. So just by pure coincidence, we happen to use 1 for all of the moles there anyway, but that's just because that happened to be what the bridge said. Next we do what goes up must come down. And I've used moles of carbon dioxide twice. I've used moles of carbonic acid twice. I can't use any moles anymore. All I have left is to find grams of that product, grams of H2CO3. When grams and moles are in the same fraction, again we go back to using 1 mole. Grams are from the periodic table. So, do that over here. We have 2 H's, 1 carbon, 3 oxygens. If you check your periodic table, the mass of hydrogen is 1.008, the mass of carbon is 12.01, and the mass of oxygen is 16. And if you add that all up, you get that the mass of carbonic acid is 62.026 grams. From here, I need to solve all my fractions, multiply it out. And we get 599, which rounds to, this 9 rounds that 9 up to a 0, which rounds this 5 up to a 6, so 0.60. And this should be grams. of H2CO3. Okay, we just did a whole lot of work. Let's make sure we know what we're doing again. This number of grams that we found from the mole bridge, remember the mole bridge was going to get us our theoretical yield. So this number that we found from the mole bridge is our theoretical yield. And what do we do with our theoretical yield? It's supposed to go on bottom of our formula. So I'm going to put that on bottom of this formula. Divide it out, multiply by 100, and we find that 85.70% is the percent yield. We're going to try another one. I know that that was a lot of stuff. Okay, we're going to try another one. Don't worry, it's okay. Let's look at number 2. Number 2 asks, what is the percent yield? Well, we know that percent yield is the actual yield over the theoretical yield times 100. Actual yield will be given to us, and theoretical yield will be from a mole bridge. We also know that yields are products, so this given one has to be a product. The theoretical yield ends as a product, but the mole bridge is going to start at a reactant. So we got to look at what they gave us here. They say 214 grams of chlorine, so chlorine is this one, 214 grams, producing 412 grams of bromine, right here. So again, when we go do our percent yield, that's actually going to be the last step that we take doing the percent yield. I know that when I do that final step and find the percent yield, my actual yield is going to be a thing that was given to me that's a product. So they gave me two things. Look at the one that's a product. This is the reactant side, this is the product side. So this one that's a product, that is my actual yield. So that's going to be what's on top by the time I'm ready to use my formula. This one that's a reactant, I'm going to use in my mole bridge to find the theoretical yield. So we're going to need 4 fractions again to go from grams of chlorine to grams of bromine, where we're starting with this 214 grams of chlorine as our given over 1, and eventually we're going to try and find a number of grams of bromine, because whatever answer we get from these 4 fractions, whatever number of grams of bromine we find, that number that we get for grams of bromine, that's going to be my theoretical yield, which is what I'm going to put down here in the bottom of my formula. Okay. Going back to my fractions, I have grams of Cl2 on top. What goes up must come down. I am not ready to use my bridge yet, because right now I have grams. My bridge is only for moles. So I can't use the bridge. Instead, I need to hopefully be able to turn this into moles so that later I can use my bridge. And if I look at that and I go, oh, I have grams and moles together in the same fraction, well, then my number of moles is 1, and my grams are going to be from the periodic table, where I need 2 chlorines. If you check your periodic table, they're each 35.45. So Cl2's mass is 70.90. Then we do what goes up must come down. And this step, where I have moles on the bottom, that's my step where I'm ready to use the arrow. So I go look at my bridge, my arrow. It's only got 1 chlorine here. No number in front means there's just 1. And if I cross the bridge, it's pointing at just 1 bromine. So we got lucky that this bridge happened to be all 1s. Then what goes up must come down. So moles of bromine are going to be on the bottom. I've now used moles of chlorine twice and moles of bromine twice. I can't use either of those again. It's time to switch to the only thing we haven't used yet, which is grams of bromine. When you have grams and moles in the same fraction, you're going to use 1 mole. Your grams are going to come from the periodic table. So for 2 bromines, each one from the periodic table is 79.90. So mass of 2 bromines is 159.8. And if we solve all our fractions, you should get 482.33 grams as your theoretical yield. That theoretical yield is supposed to go on bottom of our formula down here. So I'm going to take that answer, 482.33 grams, stick it in my formula. 412 minus 482.33. Sorry, I said minus. I meant divide. I said minus. I meant divide. Sorry. And then times 100. 85 point. You get 418, so that should round to 42%. At this time, you should be able to try the problems on page 23. And we also have a lab to do. In the next video, we'll do a pre-lab.